Welcome to this lecture series in complex numbers. In this lecture, we'll solve a problem basically. So, suppose Z1, Z2, Z3 are pairwise distinct. I mean, they're complex numbers and they are pairwise distinct. And suppose this happens. So this makes sense because Z1 and Z2 are different, so it makes sense to consider this fraction, and similarly for this and that. So, assuming this, we want to show that Z1, Z2, and Z3 are the vertices of an equilateral triangle. All right, so that's the puzzle. And now let us look at the solution. As usual, you are encouraged to pause the video and ponder upon it by yourself. All right. So let us write alpha to mean z1 minus z2, beta to mean z2 minus z3, and gamma to mean z3 minus z1. So basically we have called this as alpha, that is beta, and this is gamma. So then, first of all, forget about the hypothesis. Just if we add alpha, beta, and gamma, clearly all of this cancels out. So clearly alpha plus beta plus gamma equals 0. And by the statement of the problem, also 1 upon alpha plus 1 upon beta plus 1 upon gamma equals 0. So this was given in the question, the second one. The first one is just a triviality. The second one was given in the question, and this implies if we just clear out the denominators, we get alpha beta plus beta gamma plus gamma alpha equals 0. So let's just box out the relevant things. Oops. So that's the first box, and this is the second box. So using these two things, we have, so this is the crucial part, consider this polynomial z minus alpha, z minus beta, z minus gamma. We know this is equal to z cube minus, this is a completely general thing, this is called Vieta's theorem or something, and can be seen just by multiplying algebraically without any thought. Minus alpha, beta, gamma. So that's what you get if you expand this out. And now using that these two things are 0, we get z minus alpha, z minus beta, z minus gamma equals z cube minus alpha, beta, gamma. All right. And now this is true for each complex number z. This equation is true for each complex number z. So thus, if we substitute z equals alpha, we get 0 equals alpha cube minus alpha, beta, gamma. What happened? We just substituted z equals alpha. So here we get alpha minus alpha, then here alpha minus beta, alpha minus gamma. But alpha minus alpha is 0. And on the right side, we get alpha cube minus alpha, beta, gamma. So 0 is equal to that, and this implies alpha cube equals alpha, beta, gamma. Similar reasoning gives us that beta cube equals alpha, beta, gamma, and gamma cube equals alpha, beta, gamma. All right. But from the first one, from this one, let me label that as star. So let me call that star. So from star, what we get is the magnitude of alpha cube is equal to magnitude of alpha, beta, gamma. And similarly, so let me write that from star, we have that. And similarly, we get magnitude of beta cube is equal to magnitude of alpha, beta, gamma, and magnitude of gamma cube is equal to magnitude of alpha, beta, gamma. Separate line needed. All right, but this implies that magnitude of alpha cube is equal to magnitude of beta cube equals magnitude of gamma cube, which implies magnitude of alpha equals magnitude of beta equals magnitude of gamma. And if we just look at this last thing, what does this last thing say? This says that mod of z1 minus z2, which is magnitude of alpha, this is equal to mod of z2 minus z3, which is magnitude of beta, equals mod of z3 minus z1, which is magnitude of gamma. And therefore, the distance between z1 and z2 is equal to the distance between z2 and z3, which is equal to the distance between z3 and z1. And hence, z1, z2, z3 form the vertices of an equilateral triangle. So that finishes the proof. Let me also mention that previously we had seen a criterion, and that's an alternate way to approach this problem. Previously, we had seen a criterion that if, suppose alpha, beta, gamma are complex numbers, and this happens. So if this happens, then alpha, beta, gamma are vertices of an equilateral triangle. We are assuming that alpha, beta, gamma are pairwise distinct. So we had seen that if this happens, then alpha, beta, gamma are vertices of an equilateral triangle, and conversely, if they are vertices of an equilateral triangle, then this happens also. So one could use this and finish the problem using these two things, because once you have these two equations, you can easily show this, that this holds, and therefore alpha, beta, gamma are the vertices of an equilateral triangle. And from there, you can also conclude about z1, z2, z3. But what I did is much more straightforward, and I would say much more pleasing than using some previously proven thing. Much more direct and very nice. So I hope you were able to follow this proof. And with that, I want to end this. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.